Boundary value problems again. And here is yet another method for solving these. So far we've been focusing in on the shooting method, and in the last time in class we developed the shooting method, and we wrote a code for it, all in the notes. You can play around with that. It's very closely related to the homework. Another way to solve these boundary value problems is through what's called the direct method. And it's also a very nice alternative, especially for linear systems. So I'm going to call this direct solve, or also sometimes relaxation. Okay. Just as with the shooting methods, the shooting method relies on what? The shooting method relies on you being able to solve this thing from left to right, launch, hit, and you've got to write this algorithm to do this for you. Fine. So, you know, there's some effort involved in this. Here, same thing. You're basically going to pick a very different type of effort to put into the problem. And each one of them has its pluses and minuses for specific problems, and so it's not always clear which one you should try to use. For linear problems, this is going to be actually a pretty nice method. Okay. So is the other one, actually. It's when it gets into nonlinear problems that you have to start evaluating what do I actually want to use to solve the problem. Okay. Here's the generic problem we want to consider. Second derivative of time is equal to some function, generally nonlinear, of the function itself and its derivative with the following boundary conditions. So these are very general boundary conditions, but just as before, you can consider the general case, and what we'll do here in class is consider more specific cases. But this is the general setup. You have some nonlinear differential equation. We're going to just consider second order for now, on some domain from t goes from is in an interval a to b, and on the left you have this boundary, on the right you have this boundary. So you ask, how do I solve this? Now what we did before with the shooting method was say, okay, launch from here, solve in the interval with this, try to land there. And how do we do that? Well, we can adjust the angle of launch and things like this so that we can try to make both of these satisfied. And typically what we need is some kind of basically routine, like a bisection or otherwise. It's going to kind of lock in what angle we have to launch with to actually make this happen, to make this a reality. Okay? So fine, that's problem one. Now what we want to do is do a different approach to this, which is this direct method, which is say, okay, then let's take this, let's consider a simplified version of it, and see how we want to solve it. So we're going to consider first the linear case. Something like this with following boundary conditions. You know, so I'm going to linearize and on some interval a to b. My solution has to be here at some value alpha, over here at some value beta, and in between it's doing something, and I want to solve for that. Okay. Now, I'm going to do a different approach, and here's the interesting thing, by the way. This is why numerics is so important. This is a linear equation, second order. Non-constant coefficient. Equations like this have been around for, you know, hundreds of years, a couple centuries. In general, if you make this constant coefficient, in other words, p and q are constant, you can always solve it. As soon as you put any non-constant coefficient in there, you're pretty much, your analytic techniques are out. This is the real problem. This is the crux of the problem with differential equations, and why computing becomes so important, because there's a lot of problems where, in fact, these are non-constant coefficient. And your analytic techniques that you have available simply can't get you what you need, which is a solution to this thing. So now you turn to the computer because it's a computational problem at this point. You say, okay, well, how do I solve this? Now here's the observation you want to make. So here's a little aside, okay? So we're like in this play, we're in the middle where the action and the drama and it's all the suspense, and all of a sudden we're going to a side where the main character steps aside and does this little soliloquy about what's really going on. Okay, so you're the audience, you get to hear it. And then we come back and we slay the evil monster, which is this problem. Okay, so here's how we're going to do it. This is the sword of power, as it were, in the play. Make the following observation. I am going to Taylor expand that. Okay, so you can say, well, what does that have to do with my problem? I take a generic function at t plus delta t, and I'm going to Taylor expand it around f of t. Well, let's just write down what we get. Okay, f of t plus delta t, f prime of t plus delta t squared over 2 factorial, f double prime of t plus delta t cubed 3 factorial, f triple prime t. Actually, we're going to cut it off. We're going to do exact Taylor expansion. So instead of f triple prime t, it's f triple prime of, let's call it c1, where c1 is in the interval from t to t plus delta t. This is an exact result from Taylor's expansion theory. First few terms, remainder. Okay. The hero is still stuck. What do I do with this? But I'm going to do one other calculation, which is f of t minus delta t. Now, it's going to basically give you the same formula, except for t is going to go to minus t. Delta t is going to go to minus delta t, excuse me. So you get f of t minus delta t, f prime t, plus delta t squared, because it's squared, it stays positive, minus delta t cubed 3 factorial. Where c2 is also in this interval t to t plus delta t. Here's two observations. Here's two formulas. Now we will experience enlightenment, which will give us the keys to solving the problem here. You missed the whole beginning part where we were talking about, this is the little aside of this great play where we're slaying the monster. Okay, so anyway, that's why it's so good to be class early, because you catch all the mythological themes that are going on here. Okay, here's the observation, the enlightenment that comes from this, which is just simply, how about if I take these two equations, subtract them from each other? Watch what happens. Subtract them. What do you get? Well, this minus this gives you f of t plus delta t minus f of t minus delta t is equal to f of t. So we're subtracting this from here. That minus this is 0. That minus this gives you 2 of them. So it gives you 2 delta t f prime t. This minus this, they're the same. They subtract out to 0. And then this minus this gives me plus delta t cubed over 3 factorial f triple prime c1 plus f triple prime c2, something like this. Now, simple rearrangement. I'm going to solve for f prime in this. And here's the thing to observe. F prime, then, is equal to f of t plus delta t minus f of t minus delta t over 2 delta t minus delta t squared over 6, and then the third derivative of f valued at some c. And what I've done here is I said, look, I can use the mean value theorem. This is basically an average, right? I have the third derivative of c1 plus a third derivative of c2. I can take a 2 out of here and get some average value of c. So, okay, I'll put that average value of c here. So this here, that's all I care about for right now. There's some number. It's third derivative evaluated at some c. Some average of what the third derivative is going on. But notice what I get at the end. I have now an expression for the derivative in terms of what? In terms of a point in front and a point behind. This, in fact, is obvious. This is nothing more than a slope formula. We know that the derivative represents the slope. So if we come back here, we're trying to solve it on this interval, and we're going to break it up into a bunch of points as we go across, right, just like we did when we time-stepped it. But now with this method, we're going to break it up into a bunch of points. And if I say I want to know what the slope is at this point, then what I can do, what this says to do, is take the point in front, point behind. This is your rise over run formula. It just says take the difference over the run, which is the run of this thing is now, each one of these is delta t, and I'm going over two of them, and this gives me a slope there between these 2 points. And that's approximating the slope at that point. Okay? So a very simple calculation from this thing gives us what we need now to start thinking about solving this problem. Here's the other observation to make. How accurate is this? Delta t squared. Remember, the idea here is rise over run, and this is your correction term. This is going to be your truncation error, because we're not going to calculate this. We're going to throw this out. We're going to say, that's my slope, my approximation to the slope. What kind of error am I making? Delta t squared. So if delta t is sufficiently small, this is going towards 0. Okay? One other observation about this. You can play this game that we just did here all day long with things. You can say, instead of subtracting them, what if I would have added them? Well, if you add them, then you get this plus this. 2 of these, those 2 cancel. These 2 add together. Those 2 can cancel. And then you get the next term. And what this is going to give you then is going to give you something like the following. If you were to do this out, you'd find the following. F double prime is equal to minus f of t. Sorry, there we go. I'll tell you what you would get if you were to have added. If you add, here's what you'd get. F double prime is equal to f of t plus delta t minus 2 f of t plus f of t minus delta t all over delta t squared. Plus some truncation. Wait a minute, there's an approximation for the second derivative. You can see all I did was took these 2 formulas, which are exact, added and subtracted them. I now have an approximation for the first derivative. I have an approximation for the second derivative. Thus armed with or enlightened, our hero comes back now to the main story, which is, how do you solve this now? Given this, now it's going to be easy. Remember, all we did, and when we talked about time-stepping schemes, we were finding a way to approximate derivatives. Here are my approximate, and then you just throw that in. And in the time-stepping schemes, you approximated derivatives fairly simply by these time-stepping schemes where you basically build an iteration scheme and you can solve it forward in time. Here it's different. Here now we're saying my derivatives now are approximated by using neighbors. I want to know what's going on there. Well, what's the slope there? Well, just use rise over run formula. And the other thing you can see with this is that you can say, well, I don't necessarily need to use neighbors on either side equally. You can imagine, like, suppose I wanted to know the derivative there. I don't have any points on the right side of it. We can imagine, well, why don't I use points on the left side to somehow calculate the derivative there? And in fact, in the notes, I give you, this would be then called backward differencing. Because it'd say, let's just use the points on my left side to actually find a way to approximate a derivative there. Things like that. Okay? So in the notes, you'll find on table 2, 3, and 4. Table 2 basically says, here is the center. So by the way, this is called center differencing, when you use points equally to the left and the right. Center differencing schemes, and I give you the order delta t squared accurate schemes for the first, second, third, and fourth derivative in a table. Table 3 gives you the order delta t to the fourth accurate schemes. Okay? to make it more accurate, you keep using more and more points to your neighbors. Why not? Why just use the next two? I could use the next two after that. So you could say, well, if I really want to approximate the derivative well here, I could use the next points, but maybe the next points after that too, because maybe that'd give me a better feel with what's going on all around this point. That gives you actually delta t to the fourth accurate schemes. And finally, in table 4, we give you forward and backward differencing schemes, which you'll need to use in the homework. Okay, so now let's go ahead and plug it into here and solve. We're going to first of all discretize this whole thing up into a bunch of points. Now the nice thing is we already know, because of the boundary conditions, that if I start off here, this is going to be t0, and this is going to be my last point, t of n. We already know that y at t of 0 is equal to alpha. Because that's what I'm imposing. That's my boundary condition. I also know that y of t of n is equal to beta. Okay? Because these are nothing more than our boundary conditions. Y of a equals alpha, y of b equals beta. So all I've got to do is solve for the interior points. Solve for the remaining n-1 points. Right? Those are the interior points. I start off from 0, 1, 2, 3, all the way up to n, so there's 1 to n-1 sitting in there, and I've got to solve for what the solution is in there. Okay. How do you do that? Well, here's what we're going to do. We're going to use those formulas that we derived from Taylor expansions. Just plug them into the problem, and what you're going to find is that you're just going to get a big linear system of equations to solve. Okay, so this equation says y double prime plus, is equal to p of t, y prime plus q of t, y plus r of t. General formula, linear. Notice, okay, second derivative. Well, second derivative, I gave you the formula over there. All it says is y at t plus delta t minus 2 y of t plus y of t minus delta t all over delta t squared is equal to p of t, y prime, well, y prime is y of t plus delta t minus y of t minus delta t, plus q of t, y of t plus r of t. There you go. Just plugged everything in. And now I'm going to group things together. Okay? So first of all, look, I have y of t plus delta t terms here and here. I can also multiply everything by delta t squared, which I'm going to do. And then so what I end up getting is, what are the terms that sit in front of my y t plus delta t term? Well, I have 1 from here. I'm going to multiply by delta t squared, so it's going to be 1 from here, and then minus delta t, and this should be a 2, sorry, over 2 p of t. Okay? Now let's collect our y of t terms. There's one there. There's one here. And that's it. So we get minus 2 plus delta t squared q of t. And that comes from this one here. That one comes from this one here. Y of t plus 1 plus delta t over 2 p of t. P of t, y t minus delta t is equal to delta t squared r of t. I'm just collecting terms. So this is the coefficient of the point in front, coefficient of the point in back, coefficient of the current term, and it's equal to this. Okay, so you kind of say, well, you look at that and you go, here's the critical observation to make. Hopefully you can convince yourself easily with the algebra that that's correct. Now the big observation to make from this point is you can say that this is nothing more than big old linear system, ax equal to b. And what is a, x, and b? A, x, and b are, let's see, can I go over? No, let's go over to this board over here. All right. So that's the big question, is what are those matrices that matrices and vectors there? So first of all, the vector x is what I'm actually trying to solve for, which are the interior points. X is y of t1, y of t2, all the way to y of t n minus 1. Those are all the interior n minus 1 points. Remember, I already know what y of t0 is and y of tn is. Those are my boundary conditions. Okay? What is my matrix A then? My matrix A is, you come back over here, my matrix A says, look, for any given y of t, when I try to solve for it, it depends upon the point in front and the point behind. And these are the coefficients of those. So basically, this sets up a tridiagonal matrix. There's only three diagonals that matter in this matrix. Given a point y of t, let's say 5, y of t5, if I try to solve for it, it depends upon y of t4, and y of t6, and y of t5. Those are the only three components that matter. This is what this tells you. This is like a stencil saying, you give me a t, it depends on the point in front and behind. So when you write down your matrix A, here's what it looks like. Along the diagonals, something like this. 2 plus delta t squared, q of t1, q of t2, all the way down. And that's coming from this term right here. Okay? I'm going to do a sign change too. I'm going to multiply everything by a minus sign, just so it's going to be plus, minus, minus, minus. Okay. It's always a bad idea in class to do this, because later on you rub your face and it's there. So part of your duty, okay, is to tell me if I have black smudge. I'm on TV, remember? I got to be like a movie star. So it's very important. You tell me if I mess up. Okay, but that's that, diagonal. On the off diagonals, on the upper diagonal, you have this, 1 plus delta t over 2, p of t1, minus 1 plus delta t over 2, p of t2. The rest are zeros over here. And on the bottom diagonal, you have minus 1 minus delta t over 2, p of t2, minus 1 minus delta t over 2, p of t3, zeros. Tridiagonal structure. These two here come from, so when you multiply it by this matrix X, what it says is, so go to this generic road here. So let's look at the T2 term. The T2 term depends upon y of T1 multiplied by this and y of T3 multiplied by this. So when you take your matrix, you lay it over. So this times y of T2, this times y of T1, that times y of T3. So this is the point to the left, this is point to the right. The point to the left has this coefficients, which are given right by here. This is point to the left, t minus delta t. Point to the right has the minus sign there. Okay? And that's it. So that is your matrix A. Now, one question to see right away here is, what happened up here? Suppose I'm looking at the T1 term. The T1 term is the first point over right here. Well, when you calculate the derivative, it depends upon this point and this point. Well, this point's already known. So if this point's already known, it's going to go on the right-hand side, along with this R of t term. So let me write down then what the right-hand side b is. I'm almost out of space here, but I'll just fit one more thing down here. The vector b is equal to negative delta t squared R of t 1 plus 1 plus delta t p of t1 over 2 times y of t naught. Remember, you already know what y of t naught is. It's alpha. And the next one down is just minus delta t squared R of t2 and so forth, all the way till you get to the last ones, which are negative delta t squared R of t to the n minus 1, or sorry, n minus 2, and then finally minus delta t squared R of t to the n minus 1, and then plus 1 minus delta t over 2 p of t n minus 1 y of t n. So all the points in between have this as the right-hand side, but the two endpoints of your interval have an extra contribution. In other words, when you're calculating the derivative here or the derivative there, it relies on this point here, which is now known. It's not something you're trying to solve for. It's fixed. These are the values. So here, when you do that, you say neighboring points. Well, I already know that point. So it goes into the right-hand side, into that matrix B. Same thing here. So what's important is that you can step back from this, work out the algebra completely on some time, just to convince yourself that this is actually correct. Convince yourself that when you do this, this is what you get. The point about this is that essentially when you have a linear system of equations, it's the reason called the direct method, is because now you have this command, ax equal to b. It's a linear system of equations, and all you have to do in MATLAB is say x is equal to a backslash b. Your solution is done. That's it. No shooting, nothing. The hard work is setting up the matrices once you get them. I mean, that's the simplest command in MATLAB. Solve a linear system of equations. Now, this system might be fairly large. When we chop up this domain, if we want good accuracy, we want a very small delta t. Maybe we want, 200, 300, maybe 1,000 points between here. So when we solve this system, it's a large system. It's 1,000 by 1,000, something like that. Big deal. MATLAB still, you push return, pops it out. Okay? So this is the idea of what you want to do with a direct solve. And again, the reason it works so well is that, in this case, we're considering something linear. Now the big question, though, is, what happens if I have a nonlinear problem? Because in some sense here, we've set up this nice ax equal to b. That's really great. But if you have a nonlinear problem, you can't do this. In other words, you set it up, and then you have a way to solve it. For a nonlinear system, you're going to set something up, and you're going like, okay, now I have a nonlinear system of equations. How do you solve, in general, a nonlinear system of equations that maybe has, in fact, I have 1,000 nonlinear systems of equations all coupled together. How do I solve that in general? That can be a very difficult thing to do. Okay? So what I want to spend the remainder of the time doing is talking about, first of all, how you'd set it up nonlinearly, what the complications would be. Then talk about what are some of the techniques you actually might try to approach to actually solve this huge nonlinear system of equations. Okay? MATLAB used to have a command built into the main MATLAB toolbox called just fsolve. And fsolve basically would go through and solve you put in the nonlinear system equations and look for solutions. fsolve has now since been moved to the optimization toolbox. So you have to pay extra to get it. Okay? Now, I keep waiting for the day. I don't know if you've seen the growth of toolboxes in MATLAB, but I keep thinking there's going to come a day when it's like, oh, you wanted to plot that. Oh, well, you have to have the plotting toolbox. Oh, you wanted to solve this matrix. Well, you have to have, the linear algebra toolbox. They find ways to get more and more money. And a lot of these commands that, maybe you don't use them every day, but get shoveled into these packages. And it's kind of ridiculous that they're not in the main thing. But fsolve. So if you have the toolbox, you can use that. Otherwise, you have to think about writing your own routine or paying the bucks. I usually write my own routine. When it comes to paying bucks or just writing your own routine, I don't have the money to do it. So, all right, so let's consider a general nonlinear system, because that's really what we are after in this case. Something like this. Let's go back to our original problem formulation. So if we were to discretize the same way we did before, we'd find, here's the approximation for second derivative. And I'm going to multiply everything by delta t squared right at the beginning. Remember, there's delta t squared underneath that, but I'm going to multiply it through. And this y prime is y. So what you end up with then here is some kind of huge nonlinear system of equations. The problem is that if this is nonlinear, like in the derivative, it's not so easy necessarily to get out any kind of good you get things like y of t plus delta t squared, let's say. Well, in that case, what do you do with it? It's now you can't put it into this matrix formulation of the problem. But this here gives you some, suppose you know the boundaries. Again, an n by 1 by n by 1 nonlinear system of equations. And how do you generically solve those? And the problem with nonlinear system of equations is, first of all, you don't even know if a solution exists. That's one problem right away that you have to deal with. You don't know if the solution is unique. It's another problem to deal with. So when you start thinking about guessing solutions, or trying to get solutions to this thing, you don't know if it exists, you don't know if it's unique, and so you kind of, when you have nonlinear problems, you can have a lot of solutions, you might not have any. You don't know this at the beginning. Often, it's very important, this is very important to think about. Often what we'll do is, if you have some physical insight to the problem, you know something about the problem, you know kind of what the behavior sort of should be like. I should see, for instance, what I'm thinking is should happen to this. Let's call it a beam, let's say I deform it. It should kind of do something like this. Well, a lot of the schemes for nonlinear systems rely on putting an initial guess into the problem and letting it iterate to a solution. Well, if you know kind of what a good initial guess is, that can make or break the problem for you. Okay? But even with a really good guess, you're still not guaranteed it's going to work. All right, so that with those caveats in mind, let's talk about how to solve nonlinear systems. Or really, what I'm going to say is, let's just do, how do I solve this thing, a nonlinear root solve, for instance. I want to just solve some kind of nonlinear function and find the zeros. That's what I'm doing here. But let's just do one variable. Talk about the method for that, and then we can talk about the generalization. OK, so let's start off with something simple. We'll build it up to this general case, which may or not work, which is let's take a function, nonlinear function, say what x values make that 0. So I could plot it, for instance. Suppose my f of x looks like, well, that's the x value I'm interested in. So here's f as a function of x. I can say, well, how do I get that in general? How do I find a method that will systematically go through and find this? So probably a lot of you have heard about the Newton method or Newton-Raphson method. And here's the idea behind the Newton method. What you do is you start off with a guess. You say, I'm going to basically, what my computer does really well is iterate. And I want to find a constructive method that might be able to get me to this solution. So, and in one dimension like this, it's fairly easy. You can say, OK, how about if I take initial guess? Let me guess that it's right there. And then I can calculate what the f value is and say, oh, that wasn't a good guess. I guessed here, and actually I'm not near 0. So what the Newton method says is, okay, how do I then make another guess? And in fact, let me try to use what I've guessed to try to help me pick the next guess value. So for something like this, and let me, just for graphical purposes, I suppose that's a straight line now. What you do in the Newton method, you say, okay, from here, what I'm going to do is I'm going to use the slope of this to get me my next guess. So the slope of this is something like this. If I draw it all the way back to the 0 line, this is now going to be my next guess. Oh, well, I'm here. Got a little bit better. Now let's go off that slope. That's my x2. See, there's this process of guesses. Slope here takes me over to here. That's my x3. Slope it from here, and I get pretty dang close now. This is the process we're going to do. Always take off the slope and see where you end up on the line. Use that as your new guess value. Now, there's a lot of problems that can happen when you do this. But there is proof that says if you're sufficiently close, if you have a sufficiently good guess, it always will converge. The meaning of sufficiently close, however, is not well defined. Does that mean you have to be within 10 to the minus 6 of it? Sometimes sufficiently close means, oh man, I was a million away and it went right to it. Okay, you can be that far away and sometimes it just works beautifully. You can, or sometimes you have to be like almost exactly on top of it to work. So you can take in with a grain of salt what that means by sufficiently close. But this is the process. So let's construct the algorithm. Let's start off with just looking between x0 and x1. How did I get from x0 to x1? So first of all, right here at x0, I have a derivative. I was looking at the derivative of this thing, the slope. What is the slope? Well, the slope is just f prime at x0. That gives me the slope there. But isn't in fact slope rise over run? So we can ask, what is the rise, what is the run? Well, the rise here, right, the rise in this thing, I'm going from this point to this point. So the rise in this is from 0. So let's take this second point. It's at 0 as its rise. So the rise is from here to here minus f of x0. And the run is, there's my slope formula. So from here to here, I can say my rise is this. My run is x1 minus x0. That's what I get. That simple observation leads to the following formula. If I do this, I get x1 is equal then to x0. Just solve for x1 in this thing, minus f of x0, f prime of x0. Or more generally, you could say, well, that was just for this, but that's really the process I do for all of them. So I can generalize this just to a simple iteration of my next point is equal to what it is now, minus that. Set it up the iteration. So take your function f, take its derivative, and then just throw it into this iteration scheme. And this thing will converge if you're sufficiently close. Problems can arise. For instance, suppose I would have guessed right there. Suppose that's a 0 slope. You say, remember, the whole thing is to say, okay, go from here, take the slope back to this line. Well, if the slope is flat here, it's never getting back to that line. And in fact, you can just see this here. If this slope is 0, this thing blows up. So if you were to write an iteration program like this, you say, oh, if I hit a 0, why don't you just step over that way or this way a little bit? Then you're fine. So, you know, this is the kind of things that are built into these iteration programs, which is, if it gets to the spot where it's not supposed to be, okay, how about if I just nudge it left or right? And I'll probably be in a better spot. Okay? And then keep iterating. Things like that can happen. There are some other issues that can happen as well, but right now, that's all I want to say about the Newton-Raphson method. And it's actually one of the most generic methods for root solving that you find in the literature. Like, everybody knows, like, yeah, you just use the Newton method to solve that. Well, that's what they're talking about, because it's really easy to program. You almost have to know nothing about the problem. Okay? All right. Now, question is, how do you generalize this to what we're trying to solve here, which is this huge system of nonlinear equations? Because this will do one nonlinear equation, and what we're interested in is a system of nonlinear equations. Okay? So there's a couple ways to do it. There's a secant method and the Newton method, and these are the things that are built into this, what was built into this fsolve command, which is no longer available to you. Unless version 7 now has it, but they took it out of version 6.5, which is release 13. I'm actually downloading release 14 on my computer today, in fact, and so I'll see if it's there. If it's there, we might use it again. Otherwise, here's what you have to do. So there's basically a generalization of this. The basic scheme is going to be, this is going to be some iteration procedure you want to set up. It's going to look very similar to what we have there. What this did is says, take my current value, add something to it to generate my next piece. Same thing here. Take my current value, add something to it to get my next piece. Now what we did before, what we added here was something based upon a direction, like I'll use the slope to get me this thing. In some sense, what you do in higher dimensions is use like a gradient, the direction of flow of some nonlinear system of equations towards 0. And so what ends up happening is, how do you determine this? This is the big important piece. What is that? Well, you determine that guess from the following. You construct this matrix, the Jacobi Matrix J. I'll tell you what's in it right in a second. So you have to set up this. So each guess then is going to be determined by some x equal to b solve. Okay? Where where this function f, or this vector f, actually contains my equations. My, f of 1, f of 2, f of 3, my nonlinear system of equations are contained in here, evaluated at that current x value. So remember, you see this here, this is a chain of nonlinear systems of equations. And I can evaluate these, and it's not necessarily going to hold it. This is going to be, if I take this to the side, it's not necessarily going to be equal to 0. But if I evaluate this at some point, it's going to give me some numbers. Well, evaluate each one of these at the current point you're looking at the guess point. Yeah?
What is your notation? Delta xn over there?
What is this?
Yeah.
Delta xn is just my incremental guess.
Oh, okay.
That's all.
Okay.
There's nothing
No,
more about it. And J, by the way, what J is you take each one of these nonlinear equations, and J says, okay, it's the Jacobian, so it's f1 partial with respect to x1, f1 partial with respect to f2, f1 partial with 3, and then second equation partial with respect to f1. It's this big Jacobian matrix which basically takes the derivative of each one of these functions as a function of the variables you're actually trying to solve for, which are x1, x2, x3, x4. So it takes a little bit of work to set this up. But the nice thing is, look at an equation like this. It's tridiagonal. So the only ones that are going to matter are going to be the three diagonals. But you have to calculate them all. A derivative is a function of each of the variables. Once you have that, you can calculate this thing, and what you say is, give me a guess, x naught. Well, if I give you a guess, x naught, to start off with, what you do is you, first, evaluate this matrix J. Second, evaluate this right-hand side f. That gives you your delta x. Put it there. That gives you your x1. Now you have an x1. You come back, you evaluate this, do a linear solve, put it here, get your x2. And this is the iteration procedure you follow. What's very, very important here in general for nonlinear systems like this is you have to give it a good guess. There are some problems you can guess almost anything, and it will just converge to the solution. Those are rare. So here, what you want to guess for x naught is, what do you think the solution is going to look like? So for instance, in our homework, which we're doing a linear stuff, so we're not going to have to use this, but in our homework, we know that the eigenfunctions that we calculate for the homework, you know, the first one looks like this, second one looks like this. You could say, well, how about if I just say that's a, and I'll guess a cosine? And that kind of looks sine-ish. So these are the kind of things you might guess and then put it in here, let it try to converge to the right thing. Okay? So keep in mind, and the only reason I really give a lot about this is that it's not that uncommon to find nonlinear system equations that you're going to try to solve. You have to try to find roots for. And so this relates not only to this kind of problem, but it's a more generic feature of just things you might have to do. All right. That pretty much ends the lectures relating to sort of basic boundary value and time domain. So boundary value problems and initial value problems for ODEs. Everything we've done so far, it gives you what you need to do for the first homework, which is due 2 weeks from today. So go to town with it. I'll be in my office hours today, 2 to 3:30, and Friday, 2 to 3:30, so if you want to come by and ask questions. What we start off with tomorrow, I'm sorry, on Friday, is going to be the first lecture about what we're actually going to be doing for the second homework. And there we're going to spend a lot of time. The second homework is going to be this big, massive thing. It has a lot in it, and we're going to start off lecturing on it and go from there. So solving PDEs. Okay? All right. Have a good day. I'll see you guys.